The last thing we're going to do in this section is determining the sample size n. Now, we have seen a couple times that the margin of error in our estimate of p is given by this expression. So it's the critical z value times the what we've called the standard error of p hat. Okay, now you can see that the sample size n affects the margin of error, right? There's n there. It affects it. So if n was larger, then what happens? If I divide by a larger number, then the margin of error becomes smaller. If n is larger, then the margin of error is smaller. So that's the usual trade-off. If I want a narrower confidence interval, if I want a smaller margin of error, I need to use a larger sample, a larger n. And so if we work backwards, if we desire a certain margin of error E at a certain confidence level 1 minus alpha, then we can determine the appropriate sample size n. What we do is we solve for n. We solve for n in this relation. So how do you solve for n? Let's see. So if I divide both sides by z alpha over 2, that's a good first step. So we're just doing a bit of algebra here. Divide both sides by z alpha over 2. That will cancel out that on the right-hand side. And so now that's gone. Now what if I square both sides? So if I square both sides, let's see. So I'm going to get e squared over, actually I'll leave that in brackets, e over z alpha over 2 squared is, if I square this, then the square root is gone, right? Divided by n. Now what? Now if I, you know what, I actually do want to make this bracket go away. So I'm going to put this squared here, and this is squared down there. Good. How do I solve for n? Well, I can multiply both sides by n, and I can multiply, that will cancel there, and I can also multiply both sides by the reciprocal of that expression, and then this stuff will go away, and this is gone. So what I'm left with is n equals p hat q hat times z alpha over 2 squared e squared. So that is my that's my formula for n. But then the next thing to do is we have to round that up. It's probably not a whole number. Then we round up to the next whole number, because n has to be a whole number. Okay. Okay, and oops, just lost my place. So now think about this. Before we do a study, before we do the research, do we know what p hat is? Do we know what q hat is? No, because we haven't done a sample yet. That's the whole point. Before we take the sample, we want to figure out how many individuals to investigate. So we actually don't know p hat and q hat typically at this stage. If we do not have any idea what p hat and q hat are, a safe choice is to take just p hat is a half and q hat is 1/2. This is a safe choice. In other words, it's sort of the worst case scenario where we're going to get the biggest possible n, which is a safe choice. So then what we get is, then we get n would be 1/2 times 1/2 z alpha over 2. Let me put brackets around that to be clearer. And that would be z alpha over 2. The half times a half is 4, so I'll put the 4 down here. Okay, so this is a way, and then we round up, and then round up. So this is a formula when we don't know p hat or q hat. Okay, and in that case, the sample size is, well, I just did it here, n is that. Okay, so let's do an example with this formula. Now, if we do, okay, one more point. Sometimes we do know, sometimes we can use a p hat value and q hat from our prior knowledge, from, let's suppose, from a past study or prior knowledge, and or maybe we use what's called a pilot study, so like a small preliminary study. So we do a small study and get a rough sense of what p hat is, and then we use that value to determine what is an ideal sample size, which would probably be larger, and then we repeat with a different sample, and we can be more sure that that's an appropriate size. Okay, so or maybe in some cases there's some theoretical theory-based estimate of p hat. So for example, let's say we're testing a genetics theory that says p hat should be 1/4, and we want to test, is that actually true? Well, then we'll assume it's 1/4, and we'll calculate the sample size using that theoretical assumption. Okay, so here's an example. Just had to get a water break. Okay. Determining sample size. Question 31. So for this question, 31, use the given data to find the minimum sample size required to estimate P. Okay. So for lefties, left-handed people, find the sample size needed to estimate the percentage of California residents who are left-handed. Use a margin of error of 3 percentage points and a confidence level of 99%. Okay, so let's just say here, we are given that we should use a margin of error of 3 percentage points. 3%, but be careful here. We have to represent this as a decimal, 0.03. If I use 3, it's going to be wildly wrong. So margin of error is 0.03. And we're told that the confidence level, 1 minus alpha, is 99%. So that tells us that alpha is, what, 0.01. So what we need to do to use this, either of these formulas, we need to know the critical Z value, right? We need to know the Z alpha over 2. So alpha over 2 is 0.005. So that means the Z alpha over 2, it's the Z value that has a tail, a right tail. It has a right tail of 0.005, pretty small. So the Z value is going to be quite large. So how do we calculate that? It's norm.s.inverse of 1 minus 0.005, which is 1 minus 0.005. We did that one already, 2.57583. 2.57583. So now in part A, we're saying assume that p hat and q hat are unknown. So in that case, we're going to use the safe estimate. So we're going to use n equals z, the critical z squared over 4e squared. So it's 2.57583 squared over 4 times the margin of error squared. What do we get? I could do it in Excel, couldn't I? Let's do it in Excel. So it's equals C12 squared, that's that number, divided by 4 times 0.03 squared. Good. 1843.03. 1843.03. 1843.03. Now, we have to round it up to the next whole number, which is 1844. If I round it down, it's not quite precise enough. It's not quite enough people. Remember, the more people we have, the smaller the margin of error is. So if I have too few people, the margin of error is not going to be as small as I want it to be. So that's part A. So that's assuming that we don't know P hat and Q hat. Part B, let's say, assume that based on prior studies, 10% of Californians are left-handed. So now we're going to assume that from this earlier study, we know that P hat is 0.1, Q hat is therefore 0.9. Then the formula we could use is this one, P hat, Q hat. So instead of dividing by 4e squared, it's just divided by e squared. So what do I get? 0.1 times 0.9, 2.57583 squared over e squared, and I get 0.1 times 0.9. What do you think it's going to be, smaller or larger? Remember, the other one is what we call the safe estimate. So this is the more accurate estimate. So the safe estimate should be bigger. So we should get a smaller number here. 663.49. 663.49, which we're going to round up to 664. So that's quite a big difference, right? So using the pasts, using the second estimate would be way less time and energy, right? Asking less than about a third of the number. Second sample size is likely good enough. And it's way less time, effort, energy than the safe estimate of, so the second sample size, which was 664, is likely good enough, and it's way less resources than the safe estimate. So, I mean, these numbers matter. It'll be somebody's job to go and collect this data. Okay, now that brings us to the end of 7-1. So that was kind of a long one. And what we're getting to next is going to be sort of the same conceptual pattern, just dealing with x bar and mu instead of p hat and p. And I'll see you then.